Hey everyone, in this video we'll work on establishing an intuition for the concept of limits in calculus. Let's get right into it. Here's the graph of y equals f of x. If I ask you what f of 1 is, what would you say? Just using your basic algebra skills, you can look at the function's definition at x equals 1. There you're going to see a hole. That means the function is undefined at x equals 1, and that's our final answer. But now, you might notice something just because of your human ability to see. When you look at f of x, you can tell that the hole is sort of at x equals 1 and y equals 1. But how can you describe that with math? We've already tried using the function value, but that was a dead end. Let's try to figure out what's making us think that the hole is at y equals 1 in the first place. Let's choose a point on the graph that's to the left of x equals 1. We'll take a look at what happens when we get closer and closer to x equals 1, but never quite reaching it. Doing that, we see that the y value gets closer and closer to y equals 1, but it also never quite reaches it. We can do the same thing from the right side, and we'll see the same thing happen. As x approaches 1, y approaches 1. We can translate this idea into math through what's called a limit. Namely, we can take the limit of f of x as x approaches 1. To take this limit, we do the same analysis as before. If we let x approach 1 from both sides, we can visually see that the function is just approaching y equals 1. Thus, our limit value is just going to be 1. And that's the beauty of calculus. You can extrapolate these properties that aren't necessarily algebraically present, just like we did with the y value of the hole. I do want to emphasize how the limit didn't care about what the function actually did at x equals 1. It only cared about what the function looked like it was going to do. In the case of our graph here, despite our undefined value for f of 1, the limit itself didn't care and still had a value of 1. You can think of limits as people who only care about what you look like on the outside, not who you actually are on the inside. Don't date people who are like limits. Now we see the graph of y equals g of x. Like before, I'll just ask you what g of 1 is. I'm sure that you can see that at x equals 1, the function is defined to be 2. So g of 1 should just be 2. Shifting gears a bit, we see this hole here at x equals 1. It's practically begging to be at y equals 1, but it falls just short of that. How can we show that the hole effectively happens at y equals 1? Well, we use the power of calculus. We can take the limit of g of x as x approaches 1. As we let x approach 1 from either side, we see the function approaching y equals 1. Therefore, that's our limit value, just 1. This example once again didn't care about what the function actually did at x equals 1. Instead, the limit only cared about what the function looked like it was going to do as x approaches 1. Limits really do give you a whole new perspective on a function's properties. This time we see the graph of y equals h of x. I'll annoy you one more time and ask what h of 1 is. I'm sure we can all see it's just 1 since there's not even a hole or anything to throw us off. Now let's take the limit of h of x as x approaches 1. When x approaches 1, the function approaches y equals 1. A safe assumption for the limit then is just 1. This leads to a pretty interesting fact about the limit. We've established the principle that the limit doesn't care about what a function does, only what it looks like it's going to do. But regardless, the limit can still be equal to the function value, just like in this example. So it's important to remember that the limit could equal the function value, or it could not. Limits just kind of do whatever they want.